In this presentation, what I want to do is talk about how pipelining affects the implementation of the y86 processor. So this is the picture that we left off with when we talked about the implementation. And what I want to do is try to pull out the various pipeline stages. And if I try to do it in this picture, it's kind of tough. Like this is sort of the fetch stage, and then here's the decode stage. The ALU is up here, memory's over here, and then I have the write back phase as the edge of the register file. So it's going to be really hard to pull this apart into various pipeline stages. So I'm going to rearrange the implementation to make pipelining a little more transparent. The first thing I'm going to do is just pull apart the different pieces into their corresponding stages. So to a first approximation, we've got fetch at the bottom, and then we progress up the picture. And this will become much more clear as we build on it. The other thing I've done is I've split memory into two separate banks: instruction memory and data memory. Now, this might seem confusing because memory is really memory. And as far as like the DRAM of your computer is concerned, there's a big chunk of memory, and some of it holds instructions and some of it holds data. However, as we get close to the processor, we actually do sort of tear apart little tiny pieces of memory called caches that sort of feed the instruction stream and that feed the data stream. Now, the idea of caching will become way more transparent in the next section, but for now, when we draw this picture, it's okay that we have data memory and instruction memory separated, okay? The next thing I'm doing is I'm gathering all the state together and I'm putting it in these pipeline registers. So these pipeline registers are going to be where we hold the signals that each stage of the pipeline is going to use. The other thing I've done is I've added some error checking here. So when we talked about the regular implementation, we didn't talk about what happens if you get a bad instruction. But you can detect errors at a couple of different places. You can detect errors when you read from memory to get an instruction, because A, it might be a bad address that you're trying to read, or B, it could be a bad instruction. Maybe you thought you were getting an instruction and you actually got a random piece of data. You can also generate an error when you try to read from the data memory with a bad address. So those now show up in the picture. So this is the picture that we're going to work from to describe the pipeline implementation. Next, let's actually look at the fetch stage. You'll notice that I pulled a fast one on you and I showed you a register for decode because that's really where the first time we had all the signals. But let's look at the fetch stage. It too will have a register. And in many ways, this corresponds to the one register that we had in the sequential implementation. And there was actually some question on Piazza like, well, does that register hold the current PC or the next PC? And I didn't want to jump on that because I think it'll become much clearer right now. So what happens during the fetch stage is that we have some address from which we want to fetch, and we're going to read from memory, get an instruction, and then send that instruction through some logic that is going to then collect that logic and latch it into the decode register. So what the word latch means is it's capture the signals flowing into a register and hold them there, even if signals change below the register, sort of outside the register is going to hold those values until the next time that a clock cycle passes and we say, okay, read some new values in. Now, in the book, you'll see that in the fetch stage, it's called the next PC. And for now, I'm going to call it the calculated PC. And the reason is that when I fetch an instruction and I try to decide what the next instruction I'm going to execute is, I don't actually have all the information I might need, right? Sure, I can see how big the current instruction is and go through the PC increment, and that will tell me where the next instruction is physically in memory, but that might not be the next instruction that I'm going to execute. Now, if it's an unconditional jump, you could grab the destination or where you're going to go for the next instruction right out and you could have it. But there are some instructions where we don't actually know where the next instruction is. Can you think about what they are? Well, return has to grab something off the stack. So that's a memory read. So we certainly don't know that address. And if you have a conditional jump, you don't know whether you want to go to the next location, what we get from PC increment, or whether you're going to take the jump and you want to go where the offset says. So for the time being, we're going to call this the calculated PC, which is the best guess, which is the next PC. Or in the case of an unconditional jump or a call instruction, since we have that value from the instruction, we know that that's the next instruction. So in most cases, this calculated PC will be correct. And as we move forward over the next day or two, you'll start to see a more complicated way to compute what that next calculated PC, what the next PC is from the calculated PC. Okay, so that's our fetch stage. Next, let's look at the execution stage. And in fact, we're going to add pipeline registers at every point in the pipeline where we have a new stage. So what a stage is it's sort of the logic between two pipeline registers. And with each stage, there's a pipeline register that holds the signals that that stage is going to compute on. So everything that happens in the fetch stage is basically based on whatever values are in the fetch register. Everything that happens in the decode stage is based on exactly what's in the decode register. Similarly with execute. Now you'll notice that I don't have anything filled into the execute register because our job is going to be to figure out what goes in the execute register. So you'll also notice that I snuck in a new piece of logic, which is that when we control the ALU, we actually need to know what function the ALU is supposed to do. Is it an add, a subtract, a multiply? So we're going to have a piece of logic to figure that out. Now our job together is going to be to figure out which pieces of state from decode do we also need an execute, and which pieces of state aren't in decode that we might need an execute. So let's look at what we have in the decode register. The stat, like what happened in this instruction, is it an error? Do we need that in the execute phase? You bet. Because if in fact we've had an error, then we probably don't want to do anything in the execute stage. We're just going to pass this up until the instruction finishes. How about the I code? Well, if you remember from the implementation, we wanted that I code signal all over the processor because everybody needed it. So we need it in the execute stage too. What about ifun, the function? Well, this is actually where we really need it because we have to tell the ALU what function to execute. But what about RA and RB? Now those are register numbers. We used those in the decode stage to read the register file. But now that we're out of the decode stage, those register numbers don't actually mean anything. But instead, what we have is what the register file produced. So in the execute stage, we're actually going to need val A, what came out of the register file from A, and val B, what came out of the register file for B. Now, what about val C that we had in decode? Well, we're going to need that too. So we'll copy that up because sometimes we operate, that comes from the offset, and sometimes we have to operate on that. Now, what about val P? Val P is the value of the next program counter, but that's something that we're going to use to figure out the next PC. So we don't actually even need that in the execute stage. That's all going to be figured out in prior stages. But we do need two other pieces of information. So from the instruction point of view, RA and RB have sometimes two meanings, right? So sometimes they're the value you read out of the register file. But if we think about an ALU operation, not only do we use RB to read from the register file, we also use it way later in the write back phase to write to the register file. So we're going to introduce two new pieces of state here, dest E and dest M, right? So you remember we had little logic blocks that figured out what those are, because sometimes it's RB from the instruction, sometimes it's a stack pointer. So we still need that logic. We're going to figure out what goes into dest E and dest M, and we're going to add that to our E register. So the game here is to figure out what has to happen in a stage and that will tell you what information you need in the register. So on that note, I'm going to pause, and you're going to figure out what values you need in the latch or the pipeline register for the memory stage.